dynamics. So we say that if the Reynolds number greater than 5 times 10 to the 13, then the flow making transition to turbulent. The same thing with the Taylor number. If the Taylor number is lower than 1700, so the flow is rotating like a laminar. Okay? And then when it's greater than 1700, it becomes turbulent because you will see that there will be vortex. Vortex will generate. So that's why I say that in say for example that when we start with this atmosphere, okay, at the atmosphere because the Earth is still rotating, right? And so the atmosphere will be also moving because the Earth is rotating. And so it becomes complicated because Earth is rotating, so the atmosphere rotating, and then human being, the human activity and the ground also create this additional effect on this atmosphere. Okay, particularly if you look at the Earth's surface, you have mountain, you have plain, you have risk. Okay, so that complicated flow. So when you look at the atmosphere, the dynamic of the atmosphere is very, very challenging. And so you know that there's no long-term prediction in weather. Okay, so you know what the people in the United States do. Okay, they do it. Okay, day-by-day basis. Okay, almost day-by-day basis. Okay, and so they update. They keep updating. So usually, if you look at the weather forecast, they will okay. Today's weather is such. Okay, tomorrow such. And then they will extend it probably for 5 days. Okay, the next 5 days is such. Okay, so you will see tomorrow's prediction usually is more accurate because tomorrow's prediction is based on today's condition, right? And then the following day is based on the thing because things can change. Okay, and so what the people do is, for example, today now. You have a model based on yesterday's weather data, right? And so you know today. So once you get today's actual data, then you input that data in the computer model is the initial condition, and then predict the next 24 hours. Okay, so in that case, the next 24 hours, because you are projecting and extrapolating, so usually it's more accurate. But if you extrapolate too far, then so they have to collect it day by day. So you can see that the weather forecast in the short range is usually more accurate than the past because you have so many parameters to come by. Okay, and so that as I mentioned in rotational flow later when we talk about geometry, and that is a thing that we need to consider. Okay, because geometry when the rotational speed is very high, and then if the Taylor number is greater than 1700, then become turbulent. And when it becomes turbulent, then it changes the whole dynamics of this lubricant oil, and also is that it can induce instability. Okay, instability. So that's something that we will talk about later. Okay? Okay, anything else? Right.
So it's also related to the rotational speed.
Well, modified Reynolds number does not. I don't think we go the modified Reynolds number is no, it's not. It's not. Modified Reynolds number is related to the Reynolds number we define as usual, okay, but then has a scale. The scaling factor is z over the characteristic length for each direction. But the z is the lubricant is usually very small, in the very small. So that's ratio raised to the square, the second power makes it even smaller. So modified Reynolds number usually smaller than Reynolds number because that factor. Okay? It's not related to a location. It may be is because of that, when you look at the shearing, then when you have a shearing, when we talk about journal bearing, because journal bearing you have a shaft is rotated, right? So if you said is rotated at a certain angular velocity, then you times the radius, and you give it this shear velocity, or what is it, slipping velocity. Or if you say that you're thrust bearing, if thrust bearing you are rotating vertically, then you will have, okay? So you will look at what's the actual speed, okay? But in the slide bearing, it's simply just a translational. Okay. All right. Okay. Anything else? Okay. So, what we scheduled that originally we're going to have our second quiz or second exam this Friday, but I think we're going to push it back to next Monday. So you have a weekend to review.
No, Friday is okay.
Huh? Friday is okay?
Yeah.
Is that okay? Wait,
What you said?
Thứ hai đến thứ sáu không bảo. Này em. Cả lấy thứ hai đến thứ sáu không được.
So, what's your decision? Do you want to have it Monday or want to have Friday? Monday? Okay, so it's Monday, then we set it on Monday. Okay, and here is this. Because we are start talking about the bearing design. Okay, so they are something that I think is more practical than the regular homework part. Because when you do these design classes, you need to be familiar with the design procedure. And so, for example, in homework 3, there's a part that asks you to go through a design the process. Okay, so that will take a little bit more calculation, and so I want you to feel comfortable with those procedures. Okay, that's the main part of this class. Okay, so with that there, okay, so please get on to the homework 3 as soon as possible. Okay. Okay. So next thing that we're going to talk about is there's a called the pivoted head slider bearing. Okay, so this is different from the thing that we discussed yesterday. Yesterday we talked about this fixed incline slider bearing, and this is different. You can see from here, from the diagram, okay, it still is an inclined plane. Okay, so but the difference is that it has a pivot point. And so this plan is supported by this people, okay? And so this is an operation a little bit more flexible because, for example, here because from here, so if the load change or the flow change, okay, and so it will create a moment, okay, create a moment, and so it will change inclination, and so it can adjust better to the condition. And so this is what we call the pivoted slide plan. And so here you can see that to analyze it become more complicated because it involves all styles, and also that here if we include this side leakage because of finite side, and so there will be a slight leakage. So if you do include all this in there, then the analysis will become very, very challenging. Okay, and so instead of going through this analysis, we will simply just do that design procedure. Okay, see that how we use, okay, and how we come up with the design. Right. So here what you need to do is familiar yourself that with those term here. So that here we say that the total length of this head. Okay, so head is L, okay, and so that you can see that if this is a circle shape, then of course this L will be change is a curve, and so we can estimate this L as the distance in between the average radius times the span. Okay, and so in design it will be critical is the location of this pivot point, okay? Because where it is located, it's going to change its force balance. And also, what's involved is that number, okay? How many pads you're going to use? You're going to use in application. So there are several parameters come involved, okay? And so same thing here. This S is shoulder height, okay? But the shoulder height will change because, as I say, this when this surface, okay, the test surface rotate, then you're going to change this S, okay. And the location of this pivot point, we call it the N sub S. It's just like what we use for the parallel stick. Okay, so this N sub S indicate the location. And then here, Q is the bottom flow rate. Bottom flow rate of the lubricant. Because there's a silage, because the finite side, so there will be a silage Q sub S. Okay, so Q minus Q sub S, the silage will be the flow that through this bearing path. Okay, and so here this will represent the minimum the film thickness. That's H9. Okay. And the top surface is rotating, and the bottom surface considered in the steady operation, it will be fixed. Okay? So these are some terminology, okay, you need to understand. Okay?
You think that this bearings is fractal?
This one? No, this has been used quite common. Okay, because it is better than the fixed incline. Fixed incline plane is that once it fixed, it cannot adjust itself, adapt to the load change. And this one, it can better adapt to the load change. If you are saying, for example, load change, okay, then you can use this basis. And the other thing is that sometimes, okay, if you see the rotational speed may change direction, okay, because sometimes you may locate it in one direction. But if suddenly you change the direction, okay, the fixed incline, have a problem to adapt itself. But here, if you are working on the bi-direction, okay, if the direction can change. If you put this pivot point in the middle, right, then you can work both ways. It can work both ways. So this provides lots of flexibility in application.
This will create, I think, very dynamic moments in the environment.
Yeah. So that moment is depending on how you look at it, it's good because it's restoring. Okay, so that moment is basic is adapted to the low. Okay, and so because of that, you have this moment, so that this means that this film thickness will change. This film thickness will change according to the law. Okay, so that's the thing that it provides some flexibility. Then, but of course, there may be other things that to consider. All right. So usually, if we are using this for unidirectional, only that consider that the location is one direction, then this pivot point usually is one, located more toward the outlet. Okay, more toward outlet, so usually will not be on this side, but on this side. Okay, so that will give this minimum advantage. Right, and so it provides flexibility and also stability to the operation. So it's more than the one that we talked about yesterday about is a fixed incline. So here then when we look at is a design procedure, it's very similar to what we did yesterday. Okay, so here we think that we talked about there are two common tools we use. One is this is a diagram we call figure A, and this basically is provided is a viscosity as a function of temperature. Okay, so given temperature is shown that the viscosity for different lubricants. So here is shown that for this four types of lubricant, SAE 60. Okay, and the other is a table A. So these two are always useful. Okay, no matter it's a fixed incline or the pivoted. Okay, because this is something that we always refer to in our design calculation. Okay, so now if you look at earlier, so if given, say for example, when we start with, then we have to decide what will the geometry of the tag. And so given the geometry, length and width, then we can calculate the speed ratio, lambda. And just like what we considered yesterday, for the fixed incline, then once you know this, then you can based on your design criteria. Do you want to design it based on maximum load or minimum power consumed? Okay, so these are your choice. Okay, you want to design for minimum power, okay, or you want to design for maximum load. And so pick up one of your design goals. Okay, you have that goal in your design. Right, say for example, it's 1, then you're going up, and the read, okay, if you say that I'm going to design it for the minimum power consumption, then you will read, and that will give you the pivot location. So this will give the S, okay, so that, as I mentioned, it usually will be in 0.5 to 1, because usually it will toll outlet. So it toll outlet, so that will be 0.5 to 1, right? So that's something that you have to first determine where that location of the pivot point. All right, so once you know that, then what we do next is determine this dimensionless load function. Okay? And so now you know this pivot point, right? And this is given. So then from here, then you find out what will be the dimensionless load. Okay, so dimensional load here is in terms of square root of the dimensional load function, right? So if we outline this design procedure, then you will see that first. Okay, so the first step is that we need to determine the location of the pivot. So that means that we want to determine this S. And then to determine this, you need to know if you know the K geometry. So given the K geometry, So page geometry basic is the lambda, right? So you need to know the length and the width, okay? And then you want to know is the operation requirement. So operation requirement basic is your design code. The operation requirements of basic is 2. Okay, you want to design it for maximum load or minimum task consumption. So this is your choice. So now with this information, then we can determine the location. So what we use in this step is using the figure, I call it a PS1. Okay, so PS, you know, there is a people slider there. Okay. Alright, so this is the first step. Then once we know this, then the second step we want to determine that. Okay, so what we usually do is determine the duplication viscosity. So we want to do is determine the viscosity location, because of duplicate. Okay, and is a temperature. So usually, when you start, you don't know what will be the lubricant temperature. So you will do is based on the inlet, because what is the inlet temperature that's going to here, right? So then here, so you will say that the lubricant temperature will be the inlet temperature plus the temperature rise, okay, over 2. Okay, and so in this case, so what is needed? So you have to know, first you have to know is that, of course, lubricant type, okay, what kind of lubricant you're going to use. And then you have to know is the inlet temperature. So you have to know what is the inlet temperature. So this is the inlet temperature of lubricant. You have to keep this. Right? And so then, of course, what we don't know is the temperature rise. So unknown to us is the temperature rise. So temperature rise is something that we will determine later. Okay. So first we have to determine the viscosity. So to determine the viscosity, then we use the figure 8. So that is something like what we did before. So the fuel we use is the figure 8. So figure 8 shows that 4 lubricant. Okay, so if you use a lubricant other than those 4, then you have to go and find other information. So particularly that you can do is look at the manufacturer. Okay, the lubricant they may provide you this viscosity and temperature relation. Okay, all right. And then the third step, once we know the viscosity, then we can determine the dimensional slope. So this is in terms of capital Z, okay? And then once you know this, for example here, we use this figure PS2 to determine, okay? And so in order to do this, so what we have to know, because of this one, we have to know is that there's aspiration and then location of the people. Okay, these two have to be given, and the tool we use is the figure PS2. Right? And so because we define this load, okay, in our previous calculation, and so you can see that if you go to the inside, there's a content. It contains the film thickness. So from here, if you know this one, then we can calculate the minimum film thickness. And so to calculate this, then we can follow is using H naught. So H naught is that capital H naught times L, and then we have a load, dimension load times the viscosity times the velocity. Okay, and then okay. So here this should be instead of W, that should be V. Okay, that's okay, in the lecture note. Okay, so that's V. That's the width of the peg. And so from here, this is the H naught over S times L equals what? Capital W Z mu times U. So this is U naught, and then times V over square root. Okay, and so
I see. In this equation, the capital WZ is the load.
right. This is the load we calculate from the figure. Okay, this W is V, the width of the peg. Okay, so change correct let you know. Okay, in the lecture note that capital W is the width of the peg.
And the denominator is that the
This is a lowercase WZ. This is a dimensionless, and this is a dimensional. Okay, because we define this over this times H naught L. So if you go back to the previous page, you see the definition of this, how we normalize the load, normal load. Okay, we normalize the load, normal load is WZ. I believe that is square root of mu, V, and something else I cannot remember. Okay, so if you can check the note that we define it. So anyway, what is inside is that this the film thickness. Alright. Okay, so from here then we can calculate S. Right, so the S can be calculated as L, then WZ over mu times U naught T, then load equals 1/2. Okay. Okay, so then